Welcome to the course Computer Architecture Lab. We're going to learn in the lab how to use the Mars simulator for the MIPS chip. My name is Nachum Danzig. I'm an instructor at the Jerusalem Academic Center, or Jerusalem College of Technology, as it used to be known. So the first thing I want to show you is how to install or download the simulator that we're going to use for the course, for the lab. And the first thing you need to do is go to Google and type Java Runtime Environment. Then you will get these results, and you click on Java Runtime Environment, and you click Load. You click on Download Java Download, and you agree and start free download, and then you install it. You must do this first. Unless you already have the Java runtime environment running on your machine. You may not know that. So I don't think it will do any damage it won't do any damage. You can certainly try to download it. Again, it may not work if you already have it, but it won't do any damage. So download your Java runtime environment. You need to have this in order to run the Mars simulator, the MIPS simulator, which is called Mars. And I wouldn't recommend running the Mars without having first made sure that you have the Java, because it sometimes screws up and then it's difficult to repair it. So first, make sure you have the Java runtime environment. This is just so that the program will work. Most computers nowadays, anyway, you're probably going to want to have the Java runtime environment for Windows. This is small size, as you can see, or maybe it's larger, but whatever size it is, it's not too big, and it's worth having, and you should have it anyway, and you need to have it for the. After you've installed that, I can do it with you. Let's see if we do it. I do the download, and I run it. Now it starts to run. I said yes, but I already have it. Welcome. So I'm just going to say install, but in this case I already have it, so I'm not going to do it. But I would say, I could change the destination folder. I would say install, but in this case I'm not going to do that. Yes, I don't want to do it because I already have it. Now I go over here and I type in Mars MIPS into Google, and that will take me to this link. Now here I go and I click on that, Missouri State University. And I have to go, the funny thing is I have to press twice on download. A little bit strange. I download it, and it doesn't really download it. It just takes me to a download page. And then here I can download it. And now it starts to download. You see it's only 4 megabytes. It's a small file. Now, once I've got it downloaded, well, it takes a few seconds, I can run it. And it doesn't need installation. It just runs. You can put it on your desktop. You can cut and paste it to your desktop or not. You can leave it in its downloads, but then you'll have to go and click on it from the download folder, or you could type download in your search bar. You could type Mars in your search bar and it would find it. But you can also just go look to your download, or you can just cut and paste it to you can move it from your download folder to your desktop, and then you have it right there. Then you'll run it. Now again, first you have Java, now you run the Mars simulator, and you will get something that looks like this. You'll have a blank blue area here, a bunch of numbers over here, an area down here. Now, if I try to type a program here, it won't let me. It doesn't do anything. First thing I got to do is go to File, New, and now I have a file. And now I can type a program. For example, I would type .data if I want to make an array. And I would need to decide what type, or not what type, what length of data I'm using. Remember we talked about words and bytes? I could make an array called my array colon, and now I'd write dot, for example, word, which means store the listed values as 32-bit words on a word boundary. So that means if I write, for example, 4, it's going to be stored in a word in 4 bytes. I can therefore type also like 200,000, and I can type, for example, 36, negative 89, 17, 0, 9. There I have a bunch of words. Now each one is 4 bytes, so I have 1, 2, 3, 4, 5, 6, 7. 7 times 4 is 28. 28 bytes I've used. I can make another array. My array 2. I can give it any name I want. And I'm going to make this one bytes. So dot byte. And now I can make a number like 124, 5, 6, 7. Now 7, but now if I wanted to make, for example, 800, it would not work because a byte can have a maximum value of 127, maximum value 127 or negative 128. So if I want to put 800, I'm going to have to make my array of words. So I've made it of bytes. I got to keep the numbers small. And I have an array of bytes. Now, how many bytes did this take up? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yofi. Nice. Now I have my 2 arrays. I can make another array. My array 3. And I can say dot space. And when I say dot space, it says reserve the next specified number of bytes in the data segment. So I tell it how many bytes I want. So for example, I could say 100. That means give me 100 bytes for this array. But don't put anything in them. It's as though in C++ I would write int array of 100. But I didn't give it any numbers. Here I actually gave it numbers. And I didn't say how big it was. But it figures out how big it is. Now, how does it figure out? It counts these. And immediately after the 9, in the next byte, it's going to put the 125. And then it's going to put the 6, and then the 7, and then the 8, and then the 70. So it's adjacent. It's exactly after itself in memory. Now, if you remember, we learned that memory starts at location 400,000 hex. So this will be at 400,000 hex. This will be at 400,004, 400,008, 400,012, 400,016, 400,020, and 400,024, 400,025, 400,026, 27, 28, 29. Now, the interesting thing is, what if I would make, before this, I would make an array, let's say, my other array, and I would say dot word 4, or let's say a different number because I already used 4. Just, I don't know, 14. So where is that 14 going to be? So we said this is 124, 125 location byte, 124 to 400,024. I'll just say 24 because it's hard to say 400,024. This is at 24. Actually, in decimal, I would really have to be speaking in hexadecimal. Well, let's pretend it's in decimal. 424, 28, sorry, 25, 26, 27, 28, 29. You'd expect this to be at 30. This 14 to be at 30 and take up 4 spaces. So 30, 31, 32, and 33. But it doesn't work that way because words always start at word boundaries. It's going to, so therefore, if I this is all word bound. These are all taking up an entire word. But here, I have 1, 2, 3, 4, 5 elements here. So it takes up a word plus 1 byte. So that second word, which has only 1 byte with the 70 in it, all the other 3 bytes of that word will be ignored, will be skipped over, and the 14 will come after those 3. I can show you. I can show you that if I go like this. Now I have to. Let's compile it. If I want to compile it, I would go here to run or assemble it. And assemble is gray. I can't do it because I forgot to save it. I have to save it. Now I would suggest you make a common location where you save all your work, one folder. So I can say save, and it's going to ask me where do I want to save it. And I should save it, let's say, I could go to data, and I have a directory I already made called MIPS. I could save it there. And since I already have MIPS 1, I can call this one MIPS 2. And I can save it there. Next time I can open it. If I want to, I can run this program and then go File, Open, and go to that same location and open it again. And I can continue working from where I left off. Okay, so now we've saved it. We can compile it. I can go like, or we call it assemble. Notice the assemble is dark now, so I can assemble it. I can click on that, or there's a shortcut. I can click on this, assemble the current file. So let's do assemble. Now all of a sudden here, all of a sudden my program is missing. So it changed tabs to execute. But if I go over here to edit, I still see my program. Here is execute. And now on the bottom here, I see this whole table. This table is the actual data, the memory space in the computer. And if you notice this address, it says 100 or 10,010,000. That is the location of the I was wrong when I was saying 400,000. That's where the code sits. That whole number I said was wrong. It's not 400,000. It's 10,010,000. So it would be 10,010,000 plus. This is value. This means plus 0. In other words, this is that first word is the 4. Well, lo and behold, that's the 4 that I wrote here. The second word is 30D40. Well, that's in hexadecimal. That's actually the 20. Let's change it. I can go over here and say hexadecimal values go into decimal values. And then I see, look, it's 200,000. That's the 200,000 that I wrote here. Then there's the 36, the 89, the 17, the 0, the 9. Let's put it back in hexadecimal. The 0, the 9. Notice that these are increasing. These numbers here mean what address am I at? This is address 10,010,000 plus 0. This is 10,010,004, 10,010,008, and C, which is 12, and 10, and 14, and 18, and 1C. And then this already, the next column, the next row is 10,010,020. 20 plus 0, 24, 28. So you see, we're just going through the memory in order. Now, what should we expect to find? Well, we should expect to find, after the 9, 125. Let's see if we do. I don't know if you can see this, a bit small, but after the 9 is this byte over here. Every 2 numbers here is a byte, because every 2 numbers is a byte. So 7D is actually equivalent in hexadecimal. In 7D is 125. Let's see if that's right. I have to do some quick math in my head. 7 times 16 is 70, and 42, which is 112. I got to have another 13. 13 is D. So that's 7D is 125. So let's go back and look. And that's what it says, 7D. And then it says 6, 06, 07, 08. Well, those are the numbers that I put here. 06, 07, 08, and then 70, and then 14. So I'm just showing you that the memory the array that I created is actually sitting there in memory in the locations one after the other. After the 8, is 47. That must be 70. And then E. Notice, right, and then E. Notice that all these zeros over here. Why are there zeros over here? Why isn't the E, which is 14, right after the 70? Because that's the way I did it. Look. 14 right after the 70. It should be, I said to you, it should be in order. Why isn't the 14, the E, right after this 46, which is 70? And why are all these zeros? That's what I was explaining. It pads. It won't, if I want to add another word, it's not going to put a word and start it over here and continue it into the next row, into the next column. It's going to keep it in one column, in one group of 4. Everything starts at word boundaries, at multiples of 4. So therefore, I lost these 3 byte spaces. It's not a big deal. There's lots of bytes, but I'm just pointing out this. It's called padding. It's padding it so that the next word will start at a word boundary. If I had created this not as a word but as a byte array, then let's see what happens. Instead of me telling you, let's see what happens. Compile, and now look. After the 47 is the E right away, and there's nothing over here. Because bytes can be one after the other. There's no reason not to. It's only when I say, oh, I need a word, then it's going to start at a multiple of 4. So here I'm explaining to you a little complicated thing, which is good to know and good to help you understand when you're debugging, when you look at your memory and you want to understand what you've got. Okay, so I compile and I've got it. Now, so far what I've done is nothing. I've just created some arrays. I haven't actually done any instructions. There's no instructions here. These are just declarations of arrays. To do instructions, I need to type first .txt. Now I can write an instruction, and it will know that I mean it. Because when I write text, I'm saying following after the word text will be code, will be actual instructions. If I write the word data, I'm saying this is not instructions. These are just declarations of data. And I could, if I wanted to declare another array, I could go data and make another array, and then I could do .text again, and etc. But I don't like to do it that way. I like to have first all my arrays, then all my code. And if I want another array, all of a sudden I'll just go back up and add a line here and make a new one. So let's do something. First thing we need to do, if we're going to use this array, is get its address. Now, you could say, well, I know it. I just looked over here in the execute. Well, now I don't see it, but if I go execute, and I saw it's at address 10,010 million. I know where it is. I know where this one starts. I know where the H one starts. I can look here. But sometimes it's annoying to have to look here and find out what the number is. So we have a special command, special pseudo instruction. It's not a real instruction, but a pseudo instruction, which you're allowed to use. LA load address. And it's only for this purpose. Even though here it shows me lots of things I can do with it, we're not going to do any of them except this one. That's the only one we're going to let you use in the lab. Load address label T1, which means like a register, any register. So let's do that. Let's pick a register. Now, our registers are listed over here. These are all the registers. Some of them we don't really want to use, like the first two, 0 and AT. 0 is always 0, so we can't use it. AT is actually reserved for the assembler, which means that we're not allowed to use it. And then all the other ones we can use until we get to like, well, we could use these ones, but we're not going to use them also, these last 4. So basically we'll just use the first one we see, or I skip the V's and go to the first A. A0. A stands for argument. So I'm going to say, it doesn't really matter what you use, but I'm going to use that one. Load into register A0 the value, the address of the array called my array. Boom. Now A0 is effectively a pointer. It's pointing to the beginning of this array. And that's going to be useful if I want to access the array. Essentially, A0 is now the name of my array. This is called a label with the 2 dots after it, and that's just like a temporary name until I actually create my pointer. A0 is the real name of the array now. So now, for example, I could do load word if I want to copy something from the array into another variable. Let's say $T0 temporary. T is for temporary, T0. Now, what do I want to take? I want to take the first element. This is the way you do it. It's a little bit different from C++. First, you write the index, and then you write the pointer, the name of the array. Remember, the name of the array is a pointer to the array. So, A0. So, I've now said, go over to A0, and which is our array, the first array here, and get its first value, which is 4, and put it into T0. Let's see if that works. Run it. And it says program finished. So it ran. Now the way we can check if it worked is go over to T0. Here it is on this table. And this shows us the values. And it says 0x, which means hexadecimal, 4. Well, hexadecimal 4 is 4. So it worked. We put into T0 the value we wanted to put in. 4. I change that to 5, and when I run it, it'll be 5 over there. Now, let's say I want to put that into my other array. So I can go like this. Well, first of all, I need to have a pointer to my other array. Now, I like to organize things. So I'm going to organize it by putting both LAs over here. And I'm going to say LA A1. I'm going to use a different register for storing the address of my other array. That's where I want to copy this value into. Now, how do I do that? Well, I have the opposite command, store word. And that means go in the other direction. Take T0, we again write in the same order, but it means take T0 and go from, instead of what this was going from right to left, now we're going to go from left to right. Take that T0 and put it in the first place in the array that is pointed to by A1. So now what we should see is that in our memory, the 14 will be gone, and it will be replaced by a 4. Let's see if that really happens. Run the program. That's compile it. Now to run it, I can press this little play button. I can also go to run here and go to go. But I may as well just use the play button. So the run button. It ran. Now, how do I know if it worked? Well, I can go over to here and look. After here, remember 4 was the first value in the array? Now I see there's a 4 over here in the second array location. I remember that used to be 14. If you don't remember, I can go I can compile again, and it goes back. Now it's E. E is 14. I just compiled it again, so we're back at the beginning. And now if I go run, the E changes to a 4. So I copied it into the new array location. Now, this array is only one number. What if I were to copy it into this pointer, but not at offset 4, at 0, at offset 4? Where will it copy it to? Or will it just fail? This array has only got one element. You might say it's going to fail. How can I copy it to the second element of this array? There is no second element of the array. Well, if you remember what we said, these are all sequential. Right after this array comes this array of space. In fact, even if I wouldn't have it there, it would still, the memory is still there. There's still a memory location. So I can always write past the end of the array. I can even write past the end of this 100 because the memory is there and nobody is locking me out. I'm the only program on the computer, so I can access any memory that's not being used by the operating system. So I could keep going after this 100 even. But let's see what happens. So what I'm saying is that this 14 will not be written because I didn't write 0 here. I wrote 4. I went to the next word. Notice we don't write 1 because that would just mean that would be illegal. We would be going inside the word. We wouldn't go to the right location. We got to give it the right memory location. 4 plus, it's an addition. 4 plus this pointer. Well, this pointer is pointing to the beginning of this, so it's going to be 1 after. So I got to do 4 bytes after. So I do compile, and let's do, notice the E is here, and all these zeros are over here. Let's see what happens now. Oh, the E stays there, and the 4 goes in there. So I can put it into the space. So what I'm showing you is that I can access this space here with the other pointer, with the pointer to my other array. He can get into this one. There's enough rope to hang yourself with. You can do whatever you want. The pointers, they don't know what their domain is. They don't know how far they can point. They can point, you can just keep adding what you want, which means that you have to be careful. But let's say I don't want to do that. I want to do to 0. Let's do something. All right, let's change something here. This will be more like your homework assignment. Let's say I have my other array is now just a space. There's nothing in it, but it's just 100 spaces. And I want to copy everything in this my array into this space. Well, that's your homework assignment. So, well, with some limitations, it's supposed to stop at the 0, I believe. And I'm not going to do everything for you, but I'll show you. What I would want to do now is something like this. Again, load word $T0 for $A0. Store word $T0 for $A0. A1. So I'm copying the first one into the second one. The first one of the first array into the first place of the array pointed to by my other array of that space. Now the second one of the first array into the second space of the other array. So I can keep doing this at 4, 8, 6, but I don't know how many elements there are here. That's really dumb. I want a loop, obviously. But the problem is, in order to do a loop, I'd have to have a variable here. So you might be tempted to do something like this. Oh, I'll just put a variable here. Let's say T3. And the problem is that that's not allowed. There's no command like that. Load word does not take register, register, register. It takes 2 registers and a number. So it's illegal to do that. The compiler might let you do it. It might work because the compiler is too nice to you, but it's not really allowed. And anyway, it doesn't make sense because there's no command like that. The command load word has 2 registers. An I-type command doesn't have 3 registers. So how am I going to increment this number if I can't? So the answer is I'm not going to increment this number. I'm going to leave it as 0. I'm not going to write a 4 here or another number. I'm going to leave that as 0, but I can do something else, which is increment the pointer A0 and the pointer A1. I can move the pointers forward. So even though the index will still be the first place, the pointers themselves have moved and advanced. So I can do something like this. Add. How do you do incrementation? You take what you want. But actually, we do add I. And we're going to say $A0 is equal to $A0 and an additional 4. And I can use Control-C, Control-V, and cut and paste. And now I just have to change this from A0 to A1, A0, A1, and I've incremented them. Now all I need to do is some kind of loop, jump. You can do an unconditional loop. Think about that. Jump, start. I can call it whatever I want, but I'll call it start. And I can say, now where is my start going to go? You might say, I'll put it to start. But I don't want to load the address again because I'm actually going to increment. I'm going to change these variables. I don't want to start again at the beginning. So I only want to do that once. So I'm going to put start over here. So I don't do those things over and over again. And now I increment it, and now I load the next one, and the next one, and the next one. Now this is going to go as an infinite loop. It's never going to stop. I should obviously change something here. I need to have another condition that at some point I jump out of this area and go to a place that I'll call end. Of course, I could call it anything I want, but I'll call it end. I need to somehow get here if something happens over here. But that I leave to you for your homework. One other thing I want to point out is the temptation that a lot of people have. They want to do something like this. Load, they want to do like this. Copy from the original array to the 0th place of $A1. They want to do a command like that. Well, that would be wonderful. Just take from the old one and put it into the new one, both at the 0th place. But the problem is that you can't do that. There is no command like that. There's no load word that takes 2 registers and 2 numbers. There's only a load word that takes 1 number and 2 registers. So I can't do that. And if I would write this, just showing you things not to do. If I'd write this, it also makes no sense because then I'd be copying that number into the A1, but A1 has got a pointer in it. I'm going to overwrite my pointer and lose my pointer. I'd have to do another LA. And I don't want to write into the pointer. I want to write into the thing that the pointer is pointing to. I need to dereference. And for referencing and for dereferencing, we always use the load word and the store word. By the way, there's one more thing I want to tell you is that there's also load byte and store byte, which work the same way as load word, except then those are going to only copy a single byte, as in the other array that I created here. Now, copying a single byte is good if I have a byte array. If I have a word array, then I want to use load word. If I want to have a byte array, I want to use load byte and store byte. And the incrementation that I'm going to do is not going to be, in this case, 4, because I'm not going 4 bytes ahead each time. It's going to be just 1. I do 1 byte by 1 byte. As far as the, okay, I'll give you another video for Targil for Targil 1.2. Okay, for exercise 1.2. I'll stop here.